Hello, my name is Jinzhu Yu. I am with the Department of Civil and Environmental Engineering at Vanderbilt University. The topic of my talk today is a probabilistic network flow model for the resilience analysis of interdependent infrastructure systems. This is joint work with my advisor, Hibabaru. Modern societies are increasingly dependent on the services provided by the critical infrastructure systems, such as the water distribution systems, power grid, and communication systems. And these systems are becoming increasingly interdependent. For example, the emergency services rely on the communication systems. The electric power grid relies on the communication for control, while the communication systems depend on the power grid for electricity. One important property about the infrastructure systems is resilience, which generally refers to the ability of a system to restore its performance from disruptions. So it can be calculated by the restored performance over the initial loss of performance. For infrastructure networks, the performance is usually calculated based on the network flow or network connectivity, which is then further determined by the topological and operational attributes. However, modeling these infrastructure systems are subjected to multiple uncertainties. First, the natural hazards such as earthquakes and storms are random. Second, the vulnerability of network components are uncertain as well. Third, the system topology. By this I mean the structure of the systems after the disruptive events. Finally, the level of interdependency is also uncertain because for real-world networks, in many cases, we don't know which facilities from a network are connected to another network. And failure to account for those uncertainties can lead to increased losses and lack of resilience. Another important concept in this study is interdependence. So interdependence is a concept that describes the relationships among different systems. The seminal work about the classification of interdependence of infrastructure networks is done by Rinaldi in 2001. He categorized it into 4 types. First, physical interdependence. For example, outages in power systems cause the failures of traffic signals. Second, geographic interdependence. For example, water pipe breaks flood the nearby utility systems. Third, cyber interdependence. For example, electricity loss causes the interruption of communication systems, thereby affecting the restoration activities of power systems. Fourth, logical interdependence. One example would be outages in power systems lead to price changes of food and fuels. So far, many researchers have conducted modeling analysis about infrastructure systems based on geographic interdependency. For this study, we will focus on physical interdependence as a first step to take into different sources of uncertainty and modeling interdependence. So, to model the resilience of interdependent infrastructure networks, we developed the framework as follows. First, generate hazard intensity at each component, and then assess the component vulnerability. Next, use Monte Carlo simulation to generate a large number of failure scenarios. And then, for each time step during the recovery process, we identify damaged components and calculate the resilience based on network flow. And then some components are restored and we move on to the next step. This evaluation is repeated until the networks are fully recovered. For the methodology part, we'll focus on the identification of damaged components with considerations of the interdependence. In identifying the damaged components of interdependent networks, both physical damage and loss of supply should be considered. If the supply source is within one system, a demand node is functional as long as there is a path to the supply node. However, when the supply sources are located in 2 systems, for example, here the power network and the water network depend on each other. To determine whether or not the demand node, for example P6, is functional, we should check whether or not the supply node P4 is functional. Due to the interdependency, we should also check W3, then W4, and P7. So we have to jump back and forth between the two networks to determine the functionality of a node. The easier way to do this is to detect the functional circles, and then as soon as the node is connected to such a circle, or the node is a part of such a circle, then we can say that this node is functional. We illustrate the approach through a case study of the power and water networks of Shelby County in Tennessee. Shelby County has around 1 million population and is vulnerable to several natural hazards, such as earthquakes, storms, and flood. In the power network on the left, there are 60 nodes and 87 links. The demand nodes are substations, while the supply nodes are the gate stations. In the water network, there are 49 nodes and 71 links. The demand nodes are the intermediate delivery nodes, while the supply nodes are pumping stations. As the first step, we calculated the hazard intensity. This figure shows the intensity of an earthquake magnitude of 7.7. Since the epicenter is located northwest to Shelby County, the intensity is reduced from northwest to southeast, as represented by 5 categories here. The next step is to calculate the component vulnerability under earthquake. The failure probability of components due to physical damage is determined by the hazard intensity at the site of each component and also facility type. Comparing the hazard intensity map and the figure of failure probability, we can find that the failure probability is not proportional to the hazard intensity, indicating that the facility type also plays an important role in determining the failure probability. Then we move on to obtain the functionality of components. In this step, physical interdependency is considered, which is present when the state of one infrastructure system is dependent on the physical output of another system. For our study, we assume that the pumping stations receive electricity from the closest substations in power networks. Then the strength of interdependency is represented by the conditional probability of component I in system A fails when the component J in system B that provides supply to component I fails. Here we show the functionality of intermediate delivery nodes in the water distribution network as an example. This figure displays the difference between the mean functionality ratios with and without physical interdependency. The y-axis is the difference in mean functionality ratios. We can see that the difference increases when the interdependency strength increases from 0 to around 0.6. From the figure, we can also find that node 38, 41, 49 have very large difference between the mean functionality ratios with and without physical interdependency. These nodes are most influenced by interdependency because they have fewer connections to the supply nodes, and the interdependency link is long and therefore it is more vulnerable. We're also interested in the relationship between physical interdependency strength and distance. From the figure on the right, we can observe that under different hazard intensities, the physical interdependency strength increases with the distance. Note that physical interdependency is different from geographic interdependency because geographic interdependency decreases with the increase of distance. To sum up, we have proposed a probabilistic framework for the resilience analysis of interdependent infrastructure systems, where we model the physical interdependency. We have also investigated the impact of physical interdependency on component functionality and the relationship between physical interdependency and distance. In the future, we're going to estimate the network flow data using network centrality metrics and then incorporate the network flow to build a more accurate model. Finally, we would like to thank the National Science Foundation of US for funding this research. Thank you for watching.